Okay. Um, First, and I need to repeat this later for the other 5 or 6 people who haven't come yet. I think we'll do this remote tomorrow as well. So, and then Thursday I'll be back in the classroom for those of you who wish to come. One more person, and then start talking about the material. We are talking about sequences. It's chapter 11. I'm in section 1 at the moment, and we'll be there for a little while longer. I want to go through some WebAssign problems. If you can see the screen, you can see this computer over here. This is going to put up WebAssign problems in a little bit. I also want to talk about some of the things that are in the book. And I think maybe we should cover some of the stuff in the book first. And so I can do that in a minute. I think I'll turn on a share screen. Well, maybe before that, just I'm assuming everybody kind of knows now what sequences are. They are defined in an order. We have a first one, a second one, a third one, and so on. That's a function whose domain is the natural numbers 1, 2, 3, 4, and whose range is some set of real numbers. But we view this as a succession of things. And essentially all we have done is talked about whether or not that succession of things tends to head somewhere, and that's called a limit. And yesterday we looked at two pages of examples. Those are on 738, 739. We'll look at some more today in the WebAssign. I see one we didn't cover yesterday. Well, it's a couple we didn't cover yesterday, but one that's signed. So I'm going to put up the screen on the, let's see here. I'm not used to doing this anymore, so I'll have to get used to it again. What you should see on your screen now, I hope, is examples 8, 9, and 10. And so I get the right cursor here. This one, whenever you see a -1 to the n, that's the way we say every other one is minus. And it depends on whether you want to start at 1 or with a minus, or whether you want to start with 2, where the even ones are negative or the odd ones are negative. In this particular one, when I start out with -1 to the n, when n is 1, I have a negative. So this would start out -1 over 1. And then when n is 2, it would be plus 1/2. Then it would be -1/3, plus 1/4, -1/5, and so on. Now, this one is oscillating, is what we say. But what it's doing is it's oscillating about 0. The distance of each term to 0 decreases as the n increases. So it's jumping back and forth, and that's not figure 9, I guess. Don't know what figure it is. It's jumping back and forth between -1 and 1. Looking, somebody's waiting to come in, so I have to admit them. Anyway, so this is a new kind of thing a little bit, but it still has limit 0, and the way you can show that is take the absolute value. That gets rid of the minus businesses. That replaces the sequence with a new sequence, which is just 1 over n for all n, 1, 1/2, 1/3. We know where that goes, and since it goes to 0, that's the absolute value sequence. The original one goes to 0. So that's the theorem, which the author calls theorem 6. And that was a couple of pages back. So this example is an example of the idea that if you remove all the minuses and see what happens to what we call the absolute value sequence, if it converges to 0, then the original one does. That only works for 0. Okay, now the next theorem is very important for us because it talks about continuous functions, and what we have is a composition. This is actually a composition of 2 functions. One of them is a sequence, but a sequence is a function. And so the domain of the sequence is discrete, meaning 1, 2, 3, 4, they're spaced out. So we don't really have any limit points for any finite number. We wouldn't say n goes to 6, what happens, because it wouldn't have a limit. But infinity is an accumulation point. We've talked about that already. And the theorem says, if you have a continuous function, you can basically exchange the limit of f with f of the limit. Now this says L, but down here you'll see that he's taken the limit of something and replaced it with the sign of the limit. So he's interchanged the function and the limit sign right here. When the function is continuous, and the sign's continuous everywhere. Now the sign, if I had sine of n, it would not have a limit, but that's not the point here. The sine function is continuous. So you can not take it out like a number, but you can exchange these two orders. And so you can rewrite it in this order, look and see where this goes. If this goes someplace, which in this case it goes to 0, then the theorem says that the limit of sine of it is sine of the limit, which is 0. Okay, so that's the important application of this important theorem in terms of allowing you to jump inside and do the limit inside a continuous function. Now, this last one here in this example is a little bit harder just because it's really hard for humans to get a handle on big numbers. And n factorial, as n gets big, is really a big number. N to the n is also a really big number. And just offhand, when you think about it, I don't know which one gets bigger. Is 100 factorial bigger or smaller than 100 to the 100? And most people aren't sure. Okay, so, however, and maybe I can make it a little more obvious here. You play around. So when you don't really know much about things, sometimes it's a good idea to write down a few terms. So when I write down A1, this is what I get. When I write down A2, this is what I get. 2 times 2 in the bottom. Here we have 3, 3, 3. Here we have n, 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 and so on. Now, if you look at these, and maybe you might want to write out A4, A5, A6, maybe, because it kind of depends on when you get an idea of what you think might be happening. So maybe 3 of them is not enough. But he says it appears from these expressions and the graph in figure 10, well, that's nice, except that's not necessarily an easy thing to do. In this case, it's not so bad, but it says if you look at the graph, that's one idea. So a great idea, if you can graph these things, see what happens. Well, the graph certainly looks like they go to 0. Well, can we do that analytically? So he says here, okay, to confirm this, observe from equation 8, that's this one, okay, that I can take out 1 over n in a way. I can group these things. Somebody else want in? My screen changed. Yes, somebody else wants in. If we just group these things a bit like this, then if you notice, all the rest of these things are, this is 1, but all the rest of these things are less than 1. 2 over n, 3 over n, 4 over n, all of them less than 1. So a sub n here is less than 1 over n, because this whole big thing here is less than 1. When you multiply a number by something less than 1, it keeps the inequality. And so I presume on the next page, he's going to say it's less than 1. Let's see what happens on the next page. See if we can get this something you can see. Maybe not yet. Now you can see it. You'll notice here he says a sub n is less than 1 over n. And so we can squeeze it because it's greater than or equal to 0. And I mean, each term is positive, but the limit is going to be squeezed, go to 0. All right. Now, another very important thing has to do with powers of a fixed number. So the n is up here. That's the power. So each of these things is kind of a little sort of gem of stuff we need to know later when we do the rest of the chapter, because we'll come upon things like this and we need to know what happens. Well, what he does here is he proves that if I have something like this, if the R is, well, what do you think? If the R is 1, then this is 1, 1, 1, 1, 1, 1, 1, 1, okay? If the R is bigger than 1, like if the R is 2, then it's 2 to the n. That's 2, 4, 8, 16. That looks like it diverges. What if it's 1.01? Well, that's like a checking account or something. And these days, the checking accounts don't grow very much, but they do grow. So he says, he gives you some ideas here that he thinks that this is going to go to infinity. That's a to the x. Aha. So he's now changing n to x and trying to examine. That's one thing we can sometimes do, is change the n to x and see what happens. And anyway, if the r is bigger than 1, go to infinity. If the r is between 0 and 1, you go to 0. Okay? And he notices here that 0 to the nth power is 0, so that limits 0, and this limits 1. So we can draw some more conclusions and write less than or equal here and stuff. He says if r is less than or equal to minus 1, oh, now we're talking about negative numbers. And this diverges, as in example 7, so we could go back to that. Anyway, this example in the end gets down to this, and this you're supposed to learn. That if the r is between minus 1 and 1, then it's going to go to 0. Now, how would you do the negative number between minus 1 and 1? Well, if you put absolute value around it, that's where you use that theorem again. If the limit goes to 0, then in the absolute value business, same thing. And yeah, okay. So we're now down to a new definition. So this is like another section, really. And he defines a sequence to be increasing or decreasing or monotone. Now, I would like to increase those definitions in terms of the number of definitions. If you'll notice, we say something's increasing if, as the n gets bigger, the number gets bigger. A sub n is less than a sub n plus 1. So a sub 50 is less than a 51, and that's less than a 52, and so on. So I guess when I put my finger on it, it loses the definition. Okay. If I replace that strict inequality with less than or equal to, so if each term is less than or equal to the next one, I like to call that non-decreasing. So instead of increasing, non-decreasing, if you replace the a sub n less than with a sub n less than or equal to. Instead of decreasing, it's, if I replace this by greater than or equal to, it's non-increasing. So a non-decreasing thing is kind of going up, maybe not always, and a non-increasing thing is kind of going down. Now, if you guys have a different calculus book in high school, or if you came from someplace else and had a different book, or if you buy a different book, or if you go to the library and get a different book, or whatever, sometimes the definition that this author is saying increasing, people use the word strictly increasing. When they say strictly increasing, then non-decreasing is increasing. So in other words, some people use the word increasing for a sub n less than or equal to a sub n plus 1. Okay. And I just thought here that I didn't pin this today, but I think I don't have to at home here. Anyway, I hope the video comes out. It bothers me now, but I think we're okay. So some texts don't say what I just said. I mean, what the book says, it says increasing. I said non-decreasing, decreasing, or non-increasing. Some people will say strictly increasing, increasing, strictly decreasing, or decreasing. So you have to watch out for that. In other words, whenever you read something about increasing or decreasing, you need to go back and look at the definitions to make sure that what you are interpreting is the way it is the way it is. Now, because of that definition, the author goes and gives you some examples of increasing or decreasing sequences. Now, how can you show something is increasing or decreasing? The first way he goes here is directly. Okay. In other words, he writes 3 over n plus 5, and he writes 3 over n plus 1 plus 5. This is the a sub n plus 1. This is the a sub n. And he verifies that this one is bigger than this one because he looks and he sees what this one is. It's this one. And he says, oh, if the denominator is bigger, then the fraction is smaller. And that's what he does. So that's a literal go in and put in the nth term and the n plus first term and verify. Okay. Now, if you have a little more complicated thing, if you do the same idea here, now, one question that comes up, how did he know to do this? Why not, when you start out, why not think it's the other way? Well, the good news is it doesn't matter, meaning you decide, you might plot some terms. Like if n is 1, I will get 3 over 6. That's a half. If n is 2, I get 3 over 7. And so 3 over 6 and 3 over 7, I can see which one's bigger. So I get a guess by sticking some numbers in. I think this is decreasing. Then I try to prove this right here. But sometimes you might just start with less than. And once you work it out, you'll say, oh, I was wrong. So sometimes you can do an indirect proof because you don't know which it is, so you assume it's something. If in the end it's true, then you say I did it right. If in the end you get a contradiction, you say, oh, it must be the other way. That's because of the trichotomy law. The trichotomy law says between two numbers, either they're equal or one is less than the other. So if you know things aren't equal, one has to be less than the other, and either you're right by assuming something or you're wrong by assuming something, but if you're wrong, you'll find out what you should have assumed. So in this one, he wants to show it's decreasing, or he says show, so he's telling you, because maybe it's not so clear as to what you do. Okay, well, he does the same thing here, takes the n plus first term and the nth term and plays around with algebra. Got to make sure when you're multiplying, when you have inequalities, that the inequality doesn't change if you multiply by positive things, but be careful because you might be multiplying by a negative sometimes. And he works around, what's this double arrow thing? This means if he has this, then he gets this, or if he had that, he can go backwards. So this is an if and only thing. You can go either direction here. So he simplifies this down to here. And then he says, oh, we know this is true. Therefore, this is true, and that means this is true, this is what we want. So in this case, he simplifies down to something true. If we'd originally said greater than here, all these would be greater than. We get down here, and if you say 1 is bigger than this, I say, oh, that's not true. Therefore, you turn it around. Okay. That was, by the way, one way to do it. What's another way to do it? Change these to x's. If this is decreasing and I change these to x's, then the derivative will be negative. So what I could do is go down here and take a derivative. If the derivative is negative, then you know this is decreasing and therefore the sequence will be decreasing. So there's another way to do it. Okay, now we're going to go to something very important as far as once people got this idea down, I'm talking about in the 19th century, once they got this down in terms of understanding it, they were able to define for the first time in the history of human beings what a number is correctly, analytically, without geometry. It involves increasing sequences or decreasing sequences that are bounded. Now, if I have an increasing sequence, you know it's bounded below. Now, what does that mean? Is there a number which is smaller than everything in the sequence? And if I've got a sequence that's going up, the first term is smaller than or equal to everything else. So an increasing sequence is automatically bounded below. The question is it bounded above? Is there a number bigger than every term in the sequence? If there is, it's called bounded above. Now, if I have a decreasing sequence, it's going to be automatically bounded above. The question is it bounded below? Lastly, I might have a sequence that jumps around. But boundedness isn't dependent on whether it's going up all the time or not. Okay? Boundedness, like if I have the sine of n, sine of 1, sine of 2, sine of 3, that sequence is bounded because the sine function is bounded. That doesn't mean it converges. Okay? So convergence is not necessarily obvious just because something is bounded. However, we have a very important theorem on the next page, which says, called the monotone sequences theorem. It says every bounded monotone sequence is convergent. And that, by the way, includes the non-decreasing ones and the non-increasing ones. And it will converge to its least upper bound. Now, a least upper bound is an upper bound of everything, which is smaller than every other upper bound, smaller than or equal to. One of the properties of the real number system is that if I have, and he says at the top of the page, it's called the completeness axiom. You can see that right here, if my fingers don't get in the way. And it says a non-empty set of real numbers that has an upper bound has a least upper bound. This is what had to be learned in order to define real numbers. This property right here that I got my finger under is the most important property about numbers. Every non-empty set of real numbers that has an upper bound has a least upper bound. Now let me give you an example of that. If I have, let's consider all the numbers, and maybe I can, well, maybe we can stay on this screen, I don't know. All the numbers, let's say all the positive numbers whose square is less than 4. All the positive numbers whose square is less than 4. Well, 1 squared is less than 4. 1.5 squared is less than 4, and so on, right? So 3 squared is 9, that's not less than 4. 2.5 squared is, well, that's 5 halves squared is 25 over 4, that's 6 1/4. That's not less than 4. But there is a number which is greater than or equal to every other number in the set that we're talking about, and is the least upper bound, and that's 2. 2 is greater than or equal to anything less than 2, of course, and 2 squared is 4. It's the least number That's an upper bound of the whole set. Now, no big deal, but what if I look for all the set of all positive numbers whose square is less than 2? This numbers the square is less than 2. That's the square root of 2. Now, if we go back and start over again, suppose I talk about all the numbers, positive numbers, that are fractions, in other words, rational numbers whose square is less than 4. Then that would still give me 2. The set of all rational numbers whose square is less than 2, the point is the square root of 2 is not a member of that set. It's an example of the least upper bound not being a member of the set. In other words, square root of 2 is not a fraction, but it's the least upper bound of all the numbers whose square is less than 2. And it turns out that that is the key to how we define the square root of 2 analytically. Anyway, don't want to dwell on that too much, but this is a very important theorem. And there's one more thing in the section, then I want to go to WebAssign. And this is in WebAssign, problems like this, but this is a little harder problem. This takes a whole page to do. And let's just kind of look at it because this does occur in WebAssign. So it says investigate the sequence defined by the recurrence relation. So here's another idea. This could be a new section. It's one page, but it could be a section. So the first term is 2. The second term, that's when n is 1 here. The second term would be 1/2 of 2 plus 6. So the second term would be 4. You can see it composed down here. The third term would be 1/2 of 4 plus 6, that's 5. The fourth term is 1/2 of 5 plus 6, and so on. So we are generating a sequence from what's called a recursion, a recurrence relation. So if you ask me what's the 100th term, I have no idea. The 100th term is 1/2 the 99th term plus 6. But the 99 is 1/2 the 98th term, and so on. I'd have to do this one by one to get there, maybe. Well, nobody wants to do that. So the question is there a limit to the sequence? That's what we're in the nature of this particular section is do these sequences have limits? Do you think they head any place? And if they do head any place, can you guess where? Well, if I look at 2, 4, 5, 5.5, 5.75, 5.875, 5.9375, 5.96875, and so on, once we get all these numbers written out, it appears that I'm never going to get more than 6. Okay? And once you speculate that, once you say, hey, it looks like these numbers don't get more than 6, you could try a couple of more. You could take this number if you want to, stick it back in the formula, add 6 to it, and take 1/2. Now, if you think about it, what we're doing when we're taking a number and adding 6 and taking 1/2, we're averaging between these two numbers. So if I have 5.984375 and 6, the average between those two numbers is going to be halfway in between, right? So it's going to be bigger, but it's still going to be less than 6. So the thing is, I can look at this here without doing all this and say, hey, this is always the average. It's halfway between whatever this is and 6. And as long as this number is less than 6, this number a sub n plus 1 is also going to be less than 6 because it's halfway between, in this case, 2, it started out, and it doesn't stay with 2, it gets bigger, but it never gets bigger than 6. Okay, so you get an idea somehow. I think this might be true. So to confirm the sequence is increasing, use mathematical induction. This is another way to prove a sequence is increasing. What did we do before? We did a direct method in that one example a couple of pages back. We also did a change the function to a real valued function, took a derivative. And now we're doing a third thing, which is to prove what we believe by mathematical induction. And you go through the work here, and it's only 4 lines long. It's not very hard. Mathematical induction means you check it for the first case, then you assume it's true for the nth case and prove it's true for the n plus first case. And that's what he does. So you can look at that, and then I know it's dim, so we'll try to make it a little more bright. So what? Well, he says we need to verify it's bounded, but I already showed you that. This, no matter what, the number is less than 6, and when you take an average, it's less than 6. So 6 is an upper bound. So what we have is an increasing sequence with an upper bound. That means there is a limit. And this is kind of cool. Once I have proved there is a limit, I don't know what it is, but once I prove there is one, I call it L. And that's what he does down here. He calls the limit L. Okay? And he says, okay, when I take a limit, I know, now, this formula, he's going to stick the limit inside. And the reason is that this is a continuous function if I had an x here. So I can stick the limit inside, which he does, and I can write L here. Okay, so the limit is 1/2 of L plus 6. He says since the a sub n goes to L, it follows a sub n goes to L. And so in the end, L is 1/2 of L plus 6, and you can figure out what L is, which in this case is 6. Now, the point that is here, this is a pretty easy case situation, but the point is that once you've established that something exists, then you can use it. And that's the main part of this page is, and also proving by induction, which was new, but the main game here is once you have the existence of something, you can call it by a name and then you can work it into the problem. And so you'll have a couple of problems like that in the WebAssign pages. And I think what we should do now is go to the WebAssign pages, which is going to be for temporarily to see me. And then I'm going to go here to the WebAssign, hopefully. And okay, so 11.1, and you guys, even if you're back in chapter 10 or chapter 8 or wherever you are, you need to go up and look at these things. These are not hard, and they're so different from the last couple of chapters that you can do this and the last couple of chapters. And you just don't want to get further behind. So I'm starting out at the beginning. There's 2 videos. This is problem 3 in the exercises. And we've done this kind of stuff already. So at the beginning, I'm just going to go through the stuff and show you how easy some of it is at the beginning. You need to find a pattern. Now, this was an example in the book. And so all we're doing is redoing the example with perhaps different numbers and filling in some things. So this is an example. The next one's an example also. And you remember this one, we just talked about it already. And so you just sort of remember to go back and do the same thing again. Remember, you cut out 1 over n. That's what he does here. So this is just the example we just went through. You also have a graph so you can see where it goes. So as far as I'm concerned, this is 2 quick points. And now we also today reviewed the fact that r has to be between -1 and 1. So this is, again, just another example. And you can get 5 points, 6 points out of this one. So I know that you don't learn anything, you just want points. I'm joking now. This is easy. You just read it and answer it. And by the way, I'll tell you the answer is the last one, the first and the fourth, third one, and you can remember that because it's on video now. Okay. Then we have some things where he just wants you to get used to evaluating the sequence. These are easy. You just stick n in here and see what you get. And you see, these are the answers, of course, but notice they're pretty simple things. You just have powers of 3. No big deal, but it does alternate. So this gives you a little practice. The n-1 says the first one's going to be positive. If you remember earlier today, we had -1 to the n. That meant the first one was negative. Here we have positive. Go down here, first five terms. So we have three problems that are, I think, easy. This one is a recursion. Is this a recursion? Yes. Is this one a recursion? Yeah. No, this is not a recursion, you see. I can ask what the 100th term is here and I can figure it out. It's minus 1 over 3 to the 100th power. And you just leave it like that. You don't try to figure out what 3 to the 100th power is. You just say, oh, it's 1 over 3 to the 100th power. But here we have two recursions. That's okay because it tells you the first one. Okay. Now, here we're back to the same problem 1 again. So he's going back to the same thing he went to before. And this one, you might remember we talked about this one. But anyway, we talked about it when we were talking about something else. So if I have 2, 5, 8, 11, 14, and so on, well, how can you break down what goes on here? Well, notice if you subtract any one from the next one, you get 3. These differ by 3. Okay. And so 3 is going to be involved. 2 is 1 less than 3. 5 is 1 less than 6. 8 is 1 less than 9. What these are the remainders. When I divide a number by 3, when I get a remainder of 2, what? Just said I'd be signed out. Did you guys see that?
Yeah.
That's interesting because I'm supposed to have unlimited time. So Zoom is playing. Chinese may be unhappy. Anyway.
Nah, it's just that it likes to think that you're inactive.
I know.
So it displays that quite often.
Not on my computers. Anyway. Yeah, thank you. So I'm not xenophobic, by the way. I just tell the truth. Anyway, so this one, when you look at these numbers, they're remainders. If I had 3, 6, 9, 12, you figure it out easily. If I have 1, 4, 7, 10, see, that's just like remainder 1. So that's what they do to you sometimes. They give you multiples of something, and if there's a difference here that's always the same, you're going to have a multiple of something, plus or minus, because it's like remainders. Now this one is just, I don't know why you want to calculate the 4 decimal places. This is 1 1/4. This is a half. This is 7/8. This is, anyway, never mind. I'm old school. Plot the graphs. Okay, after you get these numbers, hopefully you can plot the graph. That bores me. What do you do with this one? I would divide by n squared all the way across the numerator and denominator. So when I do that, I get 3 over n squared. That's going to go to 0. Then this is going to go to 7. When I divide by n squared, this is going to go to 1 over n. 1 over n, where does that go? When n goes to infinity, goes to 0. And this goes to 2. So the whole thing is going to go to 7 over 2. Divide by the n squared. Okay. And if you didn't get the point, he tells you how to do it with a tutorial exercise. So you guys know, whenever you can't do something, look next to it, because maybe there's going to be a tutorial exercise coming. Then he wants you to practice. Now, when I look at this, it's going to diverge. I don't need D&E here. I know that. I don't have to have the answer book. I can look at the bottom of the screen here, and I can see this. When I have n to the 4th in the numerator and n to the cube in the denominator, when n gets big, this is going to go to infinity. Now, if you divide by n cubed, you will have n in the numerator and something that goes to 1 in the denominator. So that's what I would do that. Now, it gets a little harder here, maybe. what happens to e to a negative power? Well, that in general, the e to the negative power might go to 0, maybe. But what happens here when n gets big? When n gets big, 2 over n gets small. So this becomes e to the 0, and that's 1. Okay. Now, this one, what the idea here with all these so far has been to divide by something in numerator and denominator to see if you can figure out what goes on. Okay. So if I would divide by 3 to the n in numerator and denominator, if I would do that, I would get 1 in the numerator and 1 over 3 to the n in the denominator. That's going to go to 0. And 8 over 3 to the n, that's going to go to infinity. Because remember r, if r to a power, if the r is bigger than 1, it goes to infinity. That was in the stuff we did earlier today. And I see it's, no, I don't see. I saw it was 21 after, it's 12 after. Okay, so I can see this is going to go to 0. Another thing I could do is divide by 8 to the n, numerator and denominator. And then the denominator would be 0, go to 0 plus 1. And the numerator would be 3/8 to the n. And that r goes to 0, r to the n. So I could figure it out either way by dividing by 3 to the n, everybody, or divide by 8 to the n. Down here, looks to me like this is n squared and this is n to the 3/2. I don't worry about this 3n business. This is like n to the 3/2, and this is like n to the 4/2. So what's going to be like? It's going to be like the square root of n. It's going to go to infinity. It says do not exist, but I know that already. This one is oscillating. The denominator goes to infinity, and it's oscillating. What do you do here? You put absolute value around it, throw away the minus 1 over n. It just replaces with 1 over 3 square root n. That's going to go to 0, and therefore the original one goes to 0. We've already talked about stuff like that. Okay, so I'm just dabbling around here in the first 20. Now, one comment without doing these problems, because I want to go ahead here. There is no rule about changing this by logarithms, meaning you can't just cancel. You can't, there's no rule about the quotient of logs. The rule is the log of a quotient, but not the quotient of logs. Okay? So you don't do that. But I can write this as log 2 plus log n. And I can write this as log 6 plus log n. Okay? Once you've done that, you ought to be able to figure out how to do it. It's like what we've just done earlier, but I don't want to do all the problems for you. This one's a little more interesting just because you've got to remember some log properties first. This one, I would change to x and use L'Hopital's rule. Remember? This one, well, I think I'll leave those alone for a little while. Let's go down to the bottom here and see what's down the bottom. Okay, down the bottom here, I left them in just because you maybe want some more practice. Write out the first, or find the nth term. Okay, that was sort of like what we did before. You need to practice on how to do that. This is like multiple, see this, if I subtract, I get 4 every place. That's going to be 4n. Okay, this one, find the nth term, 2, 4, 8, that's pretty easy. Now, so let's have a couple of here just to practice. Those are a couple of easy points. You have recursions again, that we did some of those already. So some of this stuff is like going back and doing the same thing again. all the ones that say JIT are usually repeating something you did last week or something. So get beyond the JITs here. And the ones right here, I'm sorry, go here. This one, get beyond the thing, okay. Sorry, I thought it was a certain thing, it's not here. Okay, let's look at this and see what happens. Determine whether the sequence converges or diverges. 3n cosine 7n pi. Well, the n is going to go to infinity. The cosine is going to oscillate between +1 and -1. So, what do you think? And it's very quiet, but I know the answer because I can see it because I'm a teacher. But this is never bigger than 1, and this is getting huge, right? So I would guess this is going to get big. All it can do is cut 3n down a little bit. Like if cosine's a half, it's going to be 3n over 2, but n can be huge. So I would guess this is going to be infinite. Okay. Okay, we have a tutorial exercise because we have a problem like this. Determine whether a sequence converges or diverges. First of all, we have an alternating sequence. And we have an n cubed and we have an n cubed. So what's going to happen if I divide by n cubed in numerator and denominator? I'm going to get 1 up here. Down here, I'm going to get 1 plus 2 over something plus 5 over something. The denominator is going to go to 1. But I've got this thing here that the numerator has become 1. So I get 1 out of this, sort of. But it's oscillating. So you have to convince yourself that it's not going to exist. So we have a few like that. Again, find the first 5 terms, find the first 5 terms. These are easy. Just stick the numbers in. All right, here's an example of increasing, decreasing, or not monotonic. What do you think happens when you have 3n plus 1 over n? The 1 over n gets smaller, but this gets bigger. The book says it's increasing. Is it bounded? The book says it's not bounded, but you can think that out. So we have more than that. So I hope I'm not making you dizzy by going along here. So we have increasing, decreasing, several examples, you see, several kinds. So if you do try a couple of those, use a graph of the sequence. Now that's dirty because how do you know how to graph? I don't know how to graph this sequence, so I have to plot some points. Okay, but could you figure out what it's going to do? The square root is a continuous function. Square root is continuous. So the limit of the sequence of the square root is the square root of the limit. So I can go in here and forget the square root temporarily and divide by n squared. When I divide by n squared, I get 1 over n squared. That's going to go to 0, plus 6. And down here, I have 24 plus something goes to 0. So what this is going to go to inside is 1/4. Square root of 1/4 is 1/2. That's why the book, Web of Science, says the answer is a half. This problem looks to me like L'Hopital's rule, because you got something getting big here and you got it down in here in the denominator. Maybe that's a L'Hopital's rule problem. Okay, well, I have, now it is 20 after. I have been doing, I have a question for you. Is this helpful? Before you, okay. In other words, is this a good thing to do today? Anybody? Is this a terrible
Yes.
thing to do?
Yeah.
The point is, you want me to continue this kind of stuff tomorrow, we'll be talking a little bit more about stuff. What I want you to do is to do problems in 11.1, and then we can talk about any difficulties you have. I have some other stuff to talk about sequences, but I don't have to use the book, or I don't have to use WebAssign. We can do other stuff. I just thought that this might get you guys going to see how hard these problems are or not. And so I'm hoping that it's something that's been worthwhile doing today. If if you agree with that, we'll continue that tomorrow. And anybody have a thought?
Agreed.
Okay. I'm glad for that. So what I'm going to do here is I was able to take your picture today so I can see who was here and who wasn't, and I hope nobody's left. Anyway, well, so if anybody wants to stick around and say anything, I'll be happy to talk to you. Otherwise, we'll see you guys tomorrow, same time here, and we'll try to do something helpful in chapter 11. So I'll see you later.
Thank you.
Thank you.
You're welcome. Anybody hanging around is good, and we're down to 2 people, 1 person. Kenzie, are you still around? Are you wanting to talk? Kenzie's not still around.